Tonight, we turn our attention to the earliest moments of the universe, allowing the vastness of time and space to slow our thoughts. Before you get drifted away, feel free to like, subscribe. As we explore the beginnings of everything we see, we'll move gently, letting each idea unfold without urgency, like quiet starlight spreading across the sky. The phrase Big Bang refers to a state when the universe was extraordinarily hot and dense, filled with energy packed into a much smaller volume than today. Rather than an explosion outward into empty space, it describes space itself expanding everywhere at once. As expansion continued, temperatures dropped, and the universe gradually became less dense. This framework allows scientists to trace cosmic history backward using well-tested physical laws. One of the clearest signs of this expanding universe is the redshift of distant galaxies. Light traveling through expanding space has its wavelength stretched, shifting it toward redder colors. The farther a galaxy is, the more its light is redshifted, revealing that space has been growing during the light's journey. This observation forms one of the strongest foundations of modern cosmology. By combining measurements of cosmic expansion, relic radiation, and large-scale structure, scientists estimate the universe to be about 13.8 billion years old. This age is not measured directly, but inferred by fitting observations to physical models. Different methods, such as cosmic microwave background data and galaxy surveys, converge on a similar timescale. The agreement suggests a consistent cosmic timeline. At the very beginning of this timeline lies the Planck time, around 10 to the power of negative 43 seconds after the hot beginning. At such extreme conditions, known physical theories are expected to break down. Quantum gravity effects likely dominate, but no complete theory yet exists. Because of this, cosmology treats this earliest moment as a boundary of current understanding rather than a fully described era. In the earliest fractions of a second, the universe existed at energies far beyond anything achievable in laboratories. Some theories propose that the fundamental forces were unified at these energies. As expansion cooled the universe, these symmetries may have broken, causing forces to behave differently. These transitions could have left subtle imprints detectable only through careful cosmological observation. Inflation is a proposed period of extremely rapid expansion that may have occurred very early in cosmic history. During this phase, space itself would have grown exponentially in a tiny fraction of a second. Inflation helps explain why the universe appears so uniform across enormous distances. It also provides a natural way to generate the small fluctuations that later became galaxies. One motivation for inflation comes from the horizon problem. Regions of the cosmic microwave background on opposite sides of the sky have nearly identical temperatures. Without inflation, these regions would not have had time to exchange information. Inflation allows them to originate from a once-connected region before being stretched far apart. Inflation also offers an explanation for the universe's near-flat geometry. In many models, rapid expansion smooths out any initial curvature, much like inflating a balloon makes its surface appear flatter locally. This mechanism makes today's observed geometry a natural outcome rather than a finely tuned coincidence. Another appealing feature of inflation is its ability to dilute hypothetical relics, such as magnetic monopoles. Some particle theories predict these objects should exist in large numbers. Without inflation, they would be easily detectable today. Inflation spreads them so thinly that they become effectively invisible. Inflationary expansion is often described using E-foldings, which count how many times the universe's size multiplied by the mathematical constant E. Many successful models require around 50 to 60 such multiplications. The exact number depends on details like energy scale and how inflation ended. These numbers connect theory directly to observable consequences. Reheating marks the transition from inflation to the hot Big Bang phase. Energy stored in the inflation-driving field is converted into particles, filling the universe with radiation and matter. This sets the initial conditions for later cosmic evolution. The reheating temperature influences which particles are present afterward. Big Bang nucleosynthesis describes how the lightest atomic nuclei formed during the universe's first few minutes. As temperatures dropped, protons and neutrons could bind together. This brief window produced hydrogen, helium, and trace amounts of lithium. Heavier elements required later stellar processes. One of the strongest predictions of nucleosynthesis is the relative abundance of hydrogen and helium. Roughly 3/4 of ordinary matter became hydrogen, while about 1/4 formed helium-4. This ratio is remarkably consistent across different regions of the universe. Observations of primordial gas confirm this pattern. The cosmic microwave background is a faint glow left over from when the universe became transparent to light. Today, it fills all of space almost uniformly. Its average temperature is about 2.7 Kelvin, just above absolute zero. This radiation is one of the most direct pieces of evidence for a hot early universe. The spectrum of the cosmic microwave background is nearly a perfect blackbody. This means it has exactly the shape expected from radiation once in thermal equilibrium. Such precision strongly supports the idea that the early universe was hot, dense, and well mixed. Very few physical processes can create such a spectrum. Measurements by the COBE satellite confirmed this blackbody shape with extraordinary accuracy. Deviations from perfection were found to be extremely small. These results ruled out many alternative cosmological ideas. They firmly established the thermal nature of the early universe. Although the cosmic microwave background is remarkably uniform, it contains tiny temperature variations. These fluctuations are only tens of microkelvin in size. They represent small density differences present long before galaxies formed. Over billions of years, gravity amplified these differences into cosmic structure. The acoustic peaks seen in the microwave background arise from sound waves traveling through the early universe's plasma. Gravity pulled matter inward, while radiation pressure pushed outward. This created oscillations that froze in place when the universe became transparent. The resulting pattern encodes detailed information about cosmic conditions. Baryons slightly altered these sound waves by adding mass to the oscillating plasma. This baryon loading changes the heights of alternating peaks in the observed spectrum. By measuring these differences, scientists can infer the amount of ordinary matter in the universe. This provides an independent check on nucleosynthesis predictions. Polarization in the cosmic microwave background adds another layer of subtle information. E-mode polarization arises naturally from scattering in the early universe. B-mode polarization is fainter and harder to detect. Its presence could reveal gravitational waves from inflation or later gravitational lensing effects. The expanding universe causes galaxies to move apart over time, producing the observed redshift pattern. For nearby galaxies, this relationship is described by Hubble's law. This expansion is not due to galaxies moving through space, but to space itself stretching. Every observer sees a similar pattern. Early in its history, the universe was dominated by radiation rather than matter. Energy density was so high that particles collided frequently. Thermal equilibrium was maintained across vast regions. As expansion continued, the universe cooled and particle interactions became less common. As temperatures dropped, different particles ceased to be created in large numbers once thermal energy fell below their mass. Heavier species disappeared first, leaving lighter ones behind. This sequence shaped the universe's composition. Each threshold marks a transition in cosmic history. Neutrinos decoupled very early because they interact only weakly with other particles. After decoupling, they traveled freely through space. A cosmic neutrino background should still exist today. While difficult to observe directly, its effects are indirectly measured through cosmology. When electrons and positrons annihilated, their energy was transferred mainly to photons. This raised the photon temperature relative to neutrinos. As a result, photons remain slightly warmer today. This difference is a subtle but important relic of early thermal processes. A profound mystery is why matter dominates over antimatter. The observed imbalance is tiny, yet crucial. Without it, matter would have annihilated away. Explaining this asymmetry requires special physical conditions beyond simple equilibrium. Sakharov identified conditions needed to generate this imbalance. These include violations of certain symmetries and moments when equilibrium breaks down. Together, they allow small differences to accumulate. Many theories attempt to realize these conditions. Leptogenesis proposes that an imbalance among leptons appeared first. Later processes converted part of that imbalance into baryons. This idea links cosmic asymmetry to neutrino properties. It remains an active area of research. The electroweak epoch occurred when electromagnetic and weak forces behaved as one. As the universe cooled, they separated into distinct interactions. The nature of this transition affects some asymmetry models. Its details depend on particle physics beyond what is fully known. The strong force transition confined quarks into protons and neutrons. Before this, quarks moved freely in a hot plasma. Cooling caused them to bind permanently. This change altered the universe's particle makeup. As weak interactions slowed, the neutron-to-proton ratio stopped adjusting. This freeze-out fixed the number of neutrons available for later nuclear reactions. The ratio then declined slowly due to neutron decay. This balance shaped helium production. Neutrons decay with a lifetime of about 15 minutes. During the early universe, many decayed before forming nuclei. Those that survived were mostly captured into helium. This simple decay process had lasting cosmic consequences. Deuterium could not survive until temperatures dropped enough to prevent energetic photons from breaking it apart. Once this bottleneck passed, nucleosynthesis proceeded quickly. This timing was crucial for element formation. Helium-3 formed in small amounts alongside helium-4. Later stellar processes modified its abundance. This makes it harder to isolate primordial values. Still, it plays a role in consistency checks. Lithium-7 was produced in trace quantities. Observations often find less lithium than predicted. This discrepancy remains unresolved. It highlights the limits of current understanding. The baryon-to-photon ratio controls how efficiently nuclei formed. Its extremely small value reflects the universe's vast photon abundance. This ratio links early nuclear processes to present-day cosmic density. Because of nuclear stability gaps and rapid expansion, heavier elements could not form in the early universe. Carbon and oxygen required stars. This left the early cosmos chemically simple. For a long time, the universe was opaque due to constant photon scattering. Light could not travel freely. Space resembled a dense fog of radiation. Transparency came much later. Recombination allowed electrons to bind to nuclei, forming neutral atoms. This sharply reduced scattering. Light began to travel vast distances. The universe became transparent. The surface of last scattering marks where cosmic microwave background photons last interacted. It forms a spherical shell around us in time, not space. Observing it lets us glimpse early conditions. At recombination, temperatures were around a few thousand Kelvin. Expansion later cooled these photons to microwaves. This cooling reflects the universe's growth. The expansion rate is governed by equations linking geometry and energy. These equations describe how the universe evolves. They apply across cosmic history. Dark energy dominates only at late times. Early on, radiation and matter controlled expansion. Dark energy shapes the universe's future. Dark matter influenced structure long before galaxies formed. Its presence altered acoustic patterns in the microwave background. These signatures help infer its abundance. The term hot Big Bang emphasizes the early thermal state. Expansion alone is not enough to explain observations. Heat and equilibrium are essential. The Big Bang describes evolution, not ultimate origins. Questions about what came before depend on deeper theories. Current models begin with a hot state. Classical singularities indicate theoretical limits. They suggest new physics is needed. Quantum gravity may resolve them. Small early fluctuations grew into today's cosmic web. Dark matter played a central role. Baryons followed later. The observable universe is limited by light travel time. It is not the entire cosmos. Space may extend further. An event horizon can exist in an accelerating universe. It marks limits of future visibility. This boundary shapes the long-term cosmic view. As the universe continued to expand and cool beyond its earliest moments, its large-scale structure and long-term evolution began to take shape in quiet, orderly ways. After recombination, the universe entered a period often called the Cosmic Dark Ages, when neutral hydrogen filled space and no stars or galaxies yet shone. During this time, small density variations slowly grew under gravity. There were no luminous sources, but the foundations of future structure were already present. This era links the smooth early universe to the first complex objects. Matter radiation equality marks the time when matter density overtook radiation density in governing cosmic expansion. Before this point, radiation pressure limited the growth of density fluctuations. Afterward, matter could clump more efficiently. This transition strongly influenced how structures formed. Its timing is precisely constrained by observations of the cosmic microwave background. During matter domination, gravity amplified small overdensities into larger ones. Regions with slightly higher density attracted more matter over time. This gradual process laid the groundwork for galaxies and clusters. Expansion continued, but gravity gained more influence locally. The balance between expansion and attraction shaped cosmic architecture. Dark matter played a leading role in early structure formation because it does not interact with radiation. It began collapsing into halos before baryonic matter could. These halos later acted as gravitational wells. Ordinary matter fell into them after recombination. This sequence explains why galaxies form where they do. The cosmic web emerged as matter arranged itself into filaments, sheets, and voids. Dense regions became nodes where clusters formed. Large, empty regions expanded into cosmic voids. This web-like pattern reflects the growth of initial fluctuations. Modern galaxy surveys reveal this structure clearly. Baryon acoustic oscillations left an imprint on the distribution of galaxies. The same sound waves that shaped the cosmic microwave background also set a preferred separation scale in matter. This scale persists as a faint pattern in galaxy clustering. Measuring it provides a standard ruler for cosmic distances. It directly connects early plasma physics to the later universe. The sound horizon defines the maximum distance sound waves could travel before recombination. This distance depends on baryon density and expansion rate. It is measured through both the cosmic microwave background and galaxy surveys. Its consistency across epochs strengthens the Big Bang framework. It anchors much of modern cosmological distance measurement. As the universe expanded, its average temperature steadily declined. Afterward, matter cooled faster than radiation. This thermal separation shaped the Dark Ages. It also influenced how easily gas could collapse into stars. The first stars formed when dense pockets of gas collapsed under gravity. These stars likely differed from later generations, being more massive and short-lived. Their intense radiation began altering their surroundings. They marked the end of cosmic darkness. Their formation depended on conditions set much earlier. The first stars initiated reionization by emitting ultraviolet light. This light ionized surrounding hydrogen gas. Over time, expanding ionized regions overlapped. The universe gradually became ionized again. This process unfolded over hundreds of millions of years. Reionization left subtle imprints on the cosmic microwave background. Free electrons scattered some CMB photons, changing large-scale polarization. This effect allows scientists to estimate when reionization occurred. It links early star formation to primordial radiation. Observations suggest reionization was extended rather than sudden. The optical depth parameter describes how much scattering occurred after recombination. It depends on the number of free electrons along the line of sight. Measuring it helps constrain the timing of reionization. It also affects inferred amplitudes of early fluctuations. This parameter bridges early and later cosmic epochs. As stars evolved and died, they enriched the universe with heavier elements. These metals altered gas cooling properties. This allowed later generations of stars to form differently. Chemical enrichment changed the character of galaxies, yet it all began from the simple primordial composition. The near-universal presence of helium supports a Big Bang origin. Stellar processes alone cannot account for the observed baseline helium abundance. The early universe set this initial condition everywhere. Later stars only modified it slightly. This consistency reinforces nucleosynthesis predictions. The cosmic microwave background serves as a reference frame for cosmic motion. Our movement relative to it creates a dipole, anisotropy. This dipole reveals the velocity of our local group. Removing it exposes primordial fluctuations. It is a reminder that even large-scale uniformity includes subtle motion. Gravitational lensing bends the paths of cosmic microwave background photons. Matter between us and the last scattering surface distorts the observed pattern. This lensing encodes information about large-scale structure. Measuring it reveals how matter is distributed. It also provides clues about neutrino masses. The integrated Sachs-Wolf effect arises when gravitational potentials change over time. In an accelerating universe, photons gain or lose energy, crossing evolving potentials. This creates correlations between the CMB and large-scale structure. Detecting these correlations supports the existence of dark energy. It ties early radiation to late expansion. The early Sachs-Wolf effect reflects gravitational redshifts at last scattering. Photons climbing out of potential wells lose energy. This contributes to large-scale temperature variations. It directly links CMB anisotropies to early gravitational structure. This effect is strongest on the largest angular scales. The geometry of the universe influences how we interpret observations. Measurements show space is very close to flat. This result is consistent with inflationary expectations. Geometry affects angular sizes and distances. Combining datasets refines these conclusions. The cosmological principle assumes large-scale homogeneity and isotropy. Observations support this assumption when averaged over vast distances. Local structures do not contradict it. This principle simplifies cosmological modeling. It allows the universe to be described by a few parameters. Expansion history is encoded in the scale factor's evolution. Different energy components change the expansion rate differently. Radiation dominated early, matter later, and dark energy now. Each phase left observable traces. Reconstructing this history is a central goal of cosmology. Cosmic redshift reflects how much the universe has expanded since light was emitted. It provides a direct link between distance and time. Higher redshift means earlier emission. This allows astronomers to look back into cosmic history. The cosmic distance ladder builds distances step by step. Nearby measurements calibrate farther ones. Supernovae extend reach to deep cosmic time. The cosmic microwave background anchors the earliest distances. Consistency across the ladder supports the Big Bang model. Baryon density influences both nucleosynthesis and cosmic microwave background features. independent measurements agree remarkably well. This convergence strengthens confidence in early universe physics. It also limits alternative explanations. Few models achieve such consistency. The universe's expansion was decelerating for much of its history. Matter and radiation slowed expansion through gravity. Only later did dark energy reverse this trend. This change was discovered through supernova observations. It reshaped our understanding of cosmic fate. Accelerated expansion implies distant galaxies will eventually fade from view. Light emitted beyond a certain distance will never reach us. This cosmic event horizon limits future observations. It is a quiet consequence of current expansion. The Big Bang model naturally accommodates this outcome. The cosmic microwave background temperature decreases steadily as the universe expands. This cooling follows a simple scaling with redshift. Observations at different epochs confirm this behavior. It validates the interpretation of the CMB as relic radiation. This scaling is a direct thermodynamic prediction. The photon density today remains enormous compared to baryons. Hundreds of photons exist per cubic centimeter of space. This reflects the hot early state. It explains why radiation once dominated dynamics. This imbalance persists as a cosmic memory. Energy conservation in an expanding universe differs from everyday intuition. Photon energy decreases through redshift without being transferred elsewhere. General relativity describes this through space-time geometry. Local conservation holds, but global energy is not simply defined. This subtlety is fundamental to cosmology. The success of the Big Bang model comes from multiple independent lines of evidence. Expansion, relic radiation, and light element abundances each tell the same story. Their agreement is not trivial. Together, they form a coherent picture. This convergence gives the model its strength. As the universe grows older and calmer, attention turns naturally to the finer details, the subtle particles, delicate measurements, and quiet experimental clues that deepen our understanding of the Big Bang's earliest conditions. Neutrinos play a subtle but important role in cosmology because they were abundant in the early universe and interact only weakly with other matter. After decoupling, they streamed freely through space, influencing expansion and structure growth. Although they are extremely difficult to detect directly today, their presence affects observable quantities such as the cosmic microwave background and galaxy clustering. In this way, invisible particles leave measurable cosmic fingerprints. The effective number of relativistic species, often denoted as NEF, summarizes how much radiation energy existed beyond photons in the early universe. Standard physics predicts a value slightly above 3 because of neutrino behavior during electron-positron annihilation. Measurements from the cosmic microwave background and nucleosynthesis agree closely with this prediction. Any deviation would hint at new light particles or unexpected physics. The early universe's expansion rate depended sensitively on its energy content. Additional radiation would have caused faster expansion. This faster expansion would leave detectable changes in light element abundances and microwave background patterns. Because observations tightly constrain these effects, they strongly limit exotic early universe scenarios. This makes the Big Bang a powerful probe of unseen particles. Primordial density fluctuations are often described statistically through a power spectrum. This spectrum captures how much structure existed at different scales. Its nearly scale-invariant shape suggests that fluctuations were laid down by a process acting similarly across many sizes. Small deviations from perfect scale invariance provide clues about the underlying physics. These tiny differences are measured with great precision. Gaussianity describes how closely the distribution of primordial fluctuations resembles a simple random pattern. Many early universe models predict nearly Gaussian fluctuations. Observations show that deviations from Gaussianity are very small. This limits the complexity of processes that could have generated the fluctuations. Subtle statistical tests thus constrain deep cosmic history. Primordial gravitational waves, if present, would stretch and squeeze space itself. These waves could leave an imprint in the polarization of the cosmic microwave background. Detecting such a signal would offer direct insight into the energy scale of the earliest expansion. Current measurements place upper limits on their strength. Even these limits help narrow theoretical possibilities. The search for B-mode polarization is challenging because other effects can mimic it. Dust within our galaxy emits polarized light that must be carefully removed. Gravitational lensing also converts some polarization patterns into B-modes. Untangling these contributions requires sensitive instruments and multiple observing frequencies. This careful work reflects the precision needed to probe the earliest universe. Cosmological perturbations evolve differently depending on their scale. Small-scale fluctuations enter the horizon earlier and experience different physical conditions. Radiation pressure suppresses growth on very small scales. Larger scales evolve more gently. This scale-dependent behavior shapes the matter distribution we see today. The transfer function describes how primordial fluctuations were modified as the universe expanded. It accounts for horizon entry, radiation effects, and matter domination. Comparing predicted transfer functions with observations tests the Big Bang framework. These comparisons show strong agreement across a wide range of scales. This consistency connects early physics to present-day structure. Neutrino masses affect how structures grow over time. Massive neutrinos move quickly and resist clustering on small scales. This suppresses the formation of small structures slightly. Observations of galaxy clustering and lensing can detect this effect. As a result, cosmology can place limits on the total neutrino mass. The cosmic microwave background contains information not just in temperature but also in polarization correlations. Temperature polarization correlations reveal the phase relationships of early oscillations. These correlations provide independent confirmation of acoustic physics. They also help break parameter degeneracies. This layered information deepens confidence in the model. Small distortions in the cosmic microwave background spectrum could reveal energy release in the early universe. Processes such as particle decay or damping of tiny fluctuations could leave these marks. These distortions are predicted to be extremely faint. Future experiments aim to detect them. If observed, they would open a new observational window into early cosmic processes. The early universe can be described using relativistic fluid equations. Photons, baryons, and dark matter each follow coupled equations of motion. Solving these equations predicts observable patterns in the microwave background. Modern cosmology relies heavily on numerical solutions. Their success reflects the power of well-tested physical laws applied at cosmic scales. Primordial black holes are hypothetical objects that could have formed from early density fluctuations. Their possible existence depends on fluctuation amplitude at very small scales. Observations constrain their abundance through lensing and radiation signatures. Some mass ranges remain weakly constrained. Studying them tests the limits of early universe conditions. If primordial black holes were very small, they would evaporate over time through Hawking radiation. This evaporation would inject energy into the universe. Observational limits on such energy injection constrain early black hole formation. These constraints indirectly probe the small-scale fluctuation spectrum. They demonstrate how subtle effects can limit speculative scenarios. Cosmic strings are another hypothetical relic of early symmetry-breaking transitions. These one-dimensional defects would stretch across space. If present, they would distort the cosmic microwave background and produce gravitational waves. Observations place strict limits on their properties, even without detection. These limits inform theories of high-energy physics. The baryon-to-photon ratio affects recombination physics as well as nucleosynthesis. More photons mean greater ability to ionize atoms, delaying recombination. This influences the thickness of the last scattering surface. Precision modeling must account for this ratio. Its consistent value across epochs reinforces the Big Bang picture. Atomic physics plays a crucial role during recombination. Photons emitted when electrons bind to protons can reionize other atoms. Redshift gradually removes these photons from resonance. This makes recombination slower than a simple equilibrium calculation would suggest. Detailed models are required to match observations accurately. Helium recombination occurs earlier than hydrogen recombination because helium binds electrons more tightly. This changes the free electron fraction before hydrogen neutralization. Though subtle, this effect influences the cosmic microwave background damping tail. Precision observations are sensitive to it. This highlights how atomic details matter at cosmic scales. The visibility function describes when cosmic microwave background photons last scattered. It peaks around recombination and has a finite width. This width blurs small-scale anisotropies. Accurately modeling it is essential for interpreting high-resolution data. Cosmic variance limits how precisely the largest scale fluctuations can be measured. Because we observe only one universe, there are few independent large-scale modes. This introduces unavoidable uncertainty. Even perfect instruments cannot overcome it. This fundamental limit shapes how cosmologists interpret anomalies. The Sachs-Wolf effect links temperature fluctuations to gravitational potentials. Photons lose energy climbing out of potential wells. This effect dominates the largest angular scales. It provides a direct window into early gravitational structure. It is a simple yet powerful connection between gravity and radiation. Weak gravitational lensing subtly distorts images of distant galaxies. This distortion traces the distribution of matter. It depends on the same initial conditions inferred from the Big Bang. Measuring lensing helps test structure growth. It also complements cosmic microwave background lensing measurements. The cosmic neutrino background influences structure growth even without direct detection. Its free-streaming behavior suppresses clustering on small scales. This effect is encoded in the matter-power spectrum. By measuring this suppression, cosmologists infer neutrino properties. Thus, unseen particles shape visible patterns. The early universe's thermodynamics involved entropy conservation across expansion. Entropy per co-moving volume remained nearly constant after certain epochs. This conservation links early and late photon densities. It simplifies many cosmological calculations. Deviations would signal exotic processes. Freeze-out processes determine relic abundances of particles. When interaction rates drop below expansion rates, particles fall out of equilibrium. This concept applies to neutrinos, dark matter candidates, and more. The same principle explains why relic backgrounds persist. It is a unifying idea in early universe physics. Statistical isotropy means the universe looks similar in all directions on large scales. Tests of this property use cosmic microwave background maps. Most observations support isotropy within uncertainties. Small anomalies are actively studied. These tests probe the symmetry of the early universe. The matter-power spectrum records how density varies with scale. Its shape reflects both primordial fluctuations and later evolution. Comparing observations with predictions tests the entire growth history. Agreement is strong across many scales. This consistency links the Big Bang to present structure. Redshift space distortions arise from galaxy motions. These motions reflect gravitational growth. Measuring them helps infer how fast structures form. This growth rate depends on early conditions and dark energy. Thus, galaxy motions trace cosmic history. Early universe physics also affects the timing of matter radiation equality. This timing leaves imprints on the cosmic microwave background and structure formation. Shifting it would alter peak positions and clustering. Observations tightly constrain it. This limits modifications to early energy content. The cosmic microwave background's polarization angle correlations contain subtle information. They test parity and symmetry properties. Deviations could hint at new physics. So far, observations are consistent with expectations. Precision continues to improve. Laboratory measurements of nuclear reaction rates feed directly into nucleosynthesis predictions. Uncertainties in these rates propagate into element abundance estimates. Improving them refines cosmological constraints. This shows how experiments on Earth inform cosmic history. The connection is surprisingly direct. The neutron lifetime affects helium production. Small changes would shift predicted helium abundance. Cosmological observations therefore indirectly test neutron physics. Agreement supports both cosmology and laboratory measurements. This cross-check spans enormous scales. The early universe's plasma behaved like a nearly perfect fluid. Its low viscosity allowed sound waves to propagate efficiently. Photon diffusion introduced damping at small scales. These fluid properties shaped the cosmic microwave background. Their imprint remains visible today. Even tiny early universe effects can grow into measurable signals. The Big Bang model's success lies in tracing these connections carefully. Each small detail contributes to the whole. Together, they form a quiet, precise picture of cosmic beginnings. This precision allows us to listen closely to the universe's earliest whispers. As our attention drifts toward the quietest edges of cosmic understanding, these final reflections linger on the gentler, more contemplative truths of the Big Bang, where vast time and subtle physics soften into calm perspective. The Big Bang model describes a universe that began in an extremely ordered state, with remarkably smooth conditions across immense distances. This smoothness did not prevent structure from forming, but instead allowed it to grow slowly and gracefully. Tiny irregularities were enough to seed everything we see today. The balance between order and variation is one of the universe's most striking early features. The early universe's uniformity means that, on the largest scales, no place is special or central. Every region experienced the same overall expansion and cooling. This symmetry is reflected in how the cosmic microwave background looks nearly identical in every direction. Such uniformity supports the idea that the same physical laws applied everywhere from the very beginning. Expansion cooled not only radiation, but all forms of matter. As space grew, average energies declined naturally, without needing external causes. This steady cooling sets the pace for every cosmic transition. Each new form of structure emerged when conditions became calm enough to allow it. In this way, time itself became a quiet organizer of complexity. The universe's early simplicity allowed a small number of physical parameters to shape everything that followed. Quantities like expansion rate, baryon density, and fluctuation amplitude governed cosmic evolution. These few numbers determined the timing of nucleosynthesis, recombination, and structure growth. Their stability across time reflects deep underlying order. The cosmic microwave background acts as a kind of memory, preserving information from a time long before stars existed. Its photons have traveled for billions of years without forgetting their origin. They carry with them a snapshot of early conditions. Observing them is like listening to an echo that has never faded. Because the early universe was nearly in thermal equilibrium, many later calculations became simpler and more robust. Thermal processes erase complicated histories. This allows cosmologists to make precise predictions. The calm regularity of equilibrium plays a quiet but essential role in the success of the Big Bang model. The gradual transition from radiation domination to matter domination happened without drama, yet it reshaped the universe's destiny. As matter took over, gravity gained influence over structure formation. This slow handover guided galaxies into existence. It was not a sudden event, but a smooth change in balance. The formation of the first atoms marked a gentle turning point. Light, once constantly scattered, began to travel freely. Space became transparent and open. From that moment on, information could cross the cosmos unimpeded. This quiet release of light still illuminates the universe today. Even after recombination, the universe remained dark for a long time. There were no stars, no galaxies, only cooling gas and growing structure. This long silence emphasizes how patient cosmic evolution can be. Complexity did not rush into being. It waited for the right conditions. The first stars did not erase the universe's simplicity, but slowly built upon it. Their light reintroduced complexity into a once dark cosmos. Yet even then, most of the space remained empty and calm. The contrast between bright islands and vast darkness defines cosmic beauty. Helium's widespread presence reminds us that some features of the universe are primordial, not products of stars. This element was forged before any galaxy existed. Its quiet abundance links us directly to the universe's earliest minutes. It is a chemical memory shared everywhere. Hydrogen, the simplest and most abundant element, became the foundation for all later structures. Its prevalence is a direct outcome of early cosmic conditions. Stars, planets, and life rely on this early simplicity. The universe's ability to build complexity from simplicity is one of its most peaceful truths. The cosmic neutrino background, though unseen, flows gently through space. These particles rarely interact, passing quietly through galaxies and planets alike. Their existence reminds us that much of the universe is subtle and elusive. Not all cosmic influences announce themselves loudly. Dark matter, too, operates silently. It shaped structure without emitting light. Its gravitational presence guided galaxies into place. Though invisible, it played a steady, organizing role. Its quiet influence continues to sculpt the universe. Dark energy adds another layer of calm inevitability. It drives expansion without clumping or turbulence. Over time, it gently stretches space, faster and faster. This slow acceleration shapes the universe's distant future. It does so without violence or disruption. The concept of horizons introduces a soft limit to what can be known. Some regions are simply too far for light to reach us. This boundary is not abrupt, but defined by time and expansion. It reminds us that knowledge has natural edges. These edges are part of the universe's design. The cosmic event horizon suggests that the universe will become quieter over time. Distant galaxies will fade from view as expansion accelerates. The night sky will slowly empty. This future calm is a continuation of trends set long ago. Expansion carries silence with it. The steady redshifting of photons shows how expansion gently transforms energy. Light does not disappear suddenly, but stretches and cools. This process is smooth and predictable. It reflects the universe's patient consistency. Entropy increased as the universe expanded, but did so in an orderly way. The early universe had low entropy in certain respects, allowing structure to form later. This balance enabled complexity without chaos. It is a subtle foundation for cosmic evolution. The laws governing the early universe appear stable across time. Measurements from billions of years ago match physics observed today. This constancy allows us to trust backward extrapolation. It gives cosmology a calm reliability. Cosmic symmetry, broken only slightly, allowed diversity to emerge. Small asymmetries grew into galaxies and stars, yet the underlying uniformity remained. This interplay creates richness without disorder. The Big Bang model unites vast scales with simple principles. Nuclear reactions, atomic transitions, and gravitational growth all fit into one timeline. Each process plays its part without conflict. The coherence of this story is quietly reassuring. The early universe did not require fine detail to succeed. broad conditions were enough to shape everything. This robustness suggests deep natural balance. It allows cosmology to remain stable despite uncertainties. Even unresolved questions, like dark matter's identity, do not disrupt the overall calm structure of the model. They exist within well-defined boundaries. The framework remains steady while details are refined. This patience reflects scientific humility. The cosmic microwave background will continue to cool indefinitely. Its photons will grow longer in wavelength, yet they will always carry their original pattern. Time does not erase their message. Future observers, if they exist, may see a quieter universe than we do. Many galaxies will lie beyond reach. The early universe's imprints will be harder to detect. Still, the universe will remain internally consistent. The Big Bang model teaches that beginnings need not be violent to be powerful. Expansion can be gentle and transformative. Change can unfold without disruption. This perspective reshapes how we imagine origins. The universe's earliest moments were governed by simplicity, not chaos. From that simplicity emerged all later richness. This progression is slow and steady. It invites patience in understanding. Cosmic history shows that vast outcomes can arise from tiny beginnings. Small fluctuations grew into enormous structures. Nothing rushed. Everything accumulated. This slow unfolding defines cosmic time. The quiet success of the Big Bang model lies in its consistency. Independent observations agree across eras. This agreement feels less like coincidence and more like harmony. It reflects a universe that follows its rules faithfully. Looking back toward the beginning is also looking toward stillness. The farther we peer, the smoother and calmer conditions become. Complexity fades into simplicity. This reverse journey is soothing in itself. In the end, the Big Bang story is not just about heat and expansion, but about balance. Forces, particles, and time all work together without urgency. The universe took its time, becoming what it is. And as these thoughts settle, the cosmos remains vast, steady, and unhurried, expanding quietly, carrying its earliest light forward, inviting the mind to rest within its endless, gentle scale.